I make here a brief resume that of the main point that I introduced yesterday, in order to be all in the same, speaking the same language. So first of all, A will be a graded algebra with a triangular decomposition, and what this means, I recall, it is a datum of 3 subalgebras of A, right? The subalgebras, such that when you consider the tensor product of them and apply the multiplication, you obtain an isomorphism of vector space. Yes, it is an iso of vector spaces, and there is some other properties that this subalgebra has to satisfy that I don't explain. I don't write explicitly, but I suppose you have in your notes, or are in the paper of Bellamy and Thiel, for instance, that I shared today. And another algebra who play an important role in the subject is B, which is B plus. B plus is the subalgebra generated by these two subalgebras. This is in literature this is called a Borel subalgebra. And another algebra who play an important role is the negative version of this. That is the algebra generated by the A minus and T. These two algebra will play a very important role. And here is one of the main issues, is that we introduced yesterday this B bigger than 0. Oh no, bigger, smaller than 0. This is it is an ideal of B plus. Sorry, I know. B bigger than 0, and here I confuse here. B bigger than 0 is the ideal of B plus, which is defined by the homogeneous component of positive, strictly positive degree. So I take all the homogeneous component except the component of degree 0, which coincide with T, because one of the conditions of the triangular decomposition is that in degree 0 the algebra A minus and A plus is the field. So this is an ideal of B plus, and we can consider this quotient, and we obtain T because of that. I want to what I said before, that T is the component of degree 0 of B plus. And I will denote if B is in B plus, I will denote B bar the corresponding element in the quotient. And then we introduced this inflation factor, which is a factor from the category of T modules, graded or ungraded. There is no matter, any of the two categories works. And this factor goes to the category of A modules. No, B plus modules. Sorry. I will write better this. Yeah, B plus. In the following way, this factor is defined in the following way. To a module M over T, we see this the same vector space as a module over B plus with the action induced by by this projection. That means that if you take B in B plus and act by an element of M, this will equal to first apply the projection to T, and then apply the action over M, what we know how to compute, because M is a module over T. This is inflation. This is inflation because the name is because we pass from a module on T, which is also, notice that T is a subalgebra of B plus, and then we go to B plus as a model. And also we noted that this inflation induced an a bijection between the simple modules over T and the simple modules over M. These are a resume of what we see yesterday. And another important thing that that we introduced yesterday are the proper standard module. That it is a functor from the category of T modules to the category now of A modules, and which is defined in the following way: to a module over T, we associated this other module. This is the induced module of inflation. And we call this the proper standard model of M. And I finished yesterday that announcing that this when we take a M and simple module over T, this proper standard model will have a simple quotient, and this simple quotient will parameterize all the simple modules over A. This will give us a classification of the simple modules over A, of the algebra A at the beginning. So the proposal of the objective, first objective for today, is to prove this theorem. In order to prove this theorem, we will prove some lemma, and then we prove the theorem. I don't know if somebody have a question you can ask now. Okay, first I need to introduce some notation, or recall some notation maybe. And if this is a notation, a general notation for any algebra, for any module over an algebra. So there is no it is the socle, the socle of a module is defined as the maximal semisimple submodule, maximal semisimple module of M, and the radical of M is defined as the I don't want to introduce this. I want to introduce the head. The head of a module is the maximal semisimple quotient of M. These are very important objects when one studies the module of an algebra, and you can read more about this and see most of the properties that I will mention in a minute later from the book of Curtis Reiner that I send you by email this morning. Another important property of this head that I will, or the simple quotient of a module that I will use later, is that there is a bijection between the set of maximals submodules of M and there is a bijection, a natural bijection between this set and the set of simple quotients of n. So as I said before, for this bijection and also for this notation and any information or property of this model, I refer to Curtis and Reiner, the book that I send you this morning by email. Well, with this introduction, I will start to give the first step in order to prove this classification on the simple models over A. So I will start. So the first that I want to show is this lemma, which appears with lemma, which is lemma 312 according to the notation of the paper of Bellamy and Thiel that I also sent you this morning. This says the following: let S is a simple A module, and lambda will be a simple module over T, such that inflation, the inflation of lambda is a submodule of the socle of this model. Just this is so inflation, which is a module when we see lambda as B plus module. This is inflation. We are assuming that this is a submodule of what? Of the socle of S, but S as a B plus module. Here we are S is in principle an A module, but we restrict to it to a B plus model. We only consider the action of B plus. We can do that because B plus is a subalgebra of A. So if this happens, then we will prove that there exists an epimorphism from where? From the standard module of the proper standard module of lambda to S. This will be an epimorphism of A modules. So in other way, it is morphism in the category of A modules. Yeah, and that is okay. This means that this is the same that to say that S is a submodule of the head of the proper standard model. So I repeat, the assumption of the lemma is that we have a simple module. I recall that we want to classify the simple modules over A. So this lemma gives us a first information about such a modules. So if we take a simple model over A, and you take and you take a simple module over T, such that the inflation is a submodule of this S, of the socle of S as B plus module, then the lemma says that there exists an epimorphism of the proper standard module over this initial simple object. Or what is the same to say that this S of the beginning is a submodule of the head of the proper standard module, and the head of the standard module is the maximal semisimple quotient. And what we want to prove then in the lemma is that in fact this contention will be an equality. We will show that in fact the head this module is simplet, not semisimple. Are there some questions? And so I before the proof of this lemma, I will want to say something more, or to explain a little bit more of this. What is this lemma? So in other words, in other words, every simple A module is a quotient of a standard of a proper standard module for some lambda. This is another way to read this lemma, and this is because when we see S as when we see a simple module because a simple module over A ever has a simple T module as submodule. We can apply this lemma to every. In other words, if you have a simple module over A, you can find a lambda satisfying all this lemma, and then will be a quotient, and then you can apply this lemma, and the lemma say that this simple module of the beginning will be a quotient of the proper standard module. There is some question. If not, I will do the proof. We will write the proof now, which is not too difficult, because and this whole because of how we define the proper standard model, which is the inducing model. And so the proof is that we know that this inclusion another way to say this inclusion is it is equivalent to say that there exists phi morphism from inflation to the circle this morphism is in the category of B plus models. So with this, we using this phi, we can induce, because of the, I recall that the proper standard module here is an induced module from the inflation. So this is a factor, so we can apply this factor to this phi that I have right before. In other words, then we can define phi bar from the proper standard module of lambda to now to this to S. Let's follow. You have the proper standard module is a tensor product between A and M. So I take one element in each of these in A and M, and I send them to A acting in phi of M. Phi is the morphism given by the inclusion. So this is a. I have a question. That phi is unique? No, this phi is not unique in the proof, but there exists. There exists because the assumption is that we have a contention. But there is no matter if it's unique or not. The existence is the only what we needed. Okay, and this bar phi is a morphism in the category of A modules. And now I will, and this morphism is surjective. Let me say that it is why is surjective, and this finished the proof. So where I can write, then note that I can erase here in order to have all the proof together. Oh, here I will write here. Now here I follow here the proof. So notice that phi is non-zero morphism because phi bar is not zero because phi is not zero. And then, as this morphism is not zero, has to be an epimorphism because S is simple. And simple means that there is not non-trivial submodules. And this ends the proof of the lemma. We find an epimorphism from the proper standard module to S. Oh. Yeah, okay. Yeah, okay. This finished the proof of the lemma, and we will prove the theorem and write the theorem. The recording of yesterday, I think, will be in the future. It's not possible to watch now. If you have any question, you can ask me. Gumor. But if not, you can you can see all what I say. You can read the paper of Bellamy and Thiel that I send you by email, and most of the things that I mentioned are there, and I follow the same notation. And you can write me if you have any question. So now I will write the theorem, and then we will prove it. Yeah, when I say that S is in RC, this means that S is simple, because I recall that these denote the simple modules, the set of simple modules over A. Here I will write here. Yeah, that is we will prove now. We will prove now that the head is simple. We just what we prove it is that every simple module is a quotient of the proper standard module. What we will prove now is that each proper standard module has only one simple quotient. That we will prove now. Okay, so I will write the theorem now. This is the theorem. This is part of the theorem T13, because I split the results in two steps in order to introduce. That is only if you see the paper and see this theorem. The theorem has more points, but we will prove only one part now. So what we will prove? We will prove the following: if lambda is a simple module over T, then we will prove that the head of the proper standard module of lambda is simple. That means that this belongs to this set, the set of simple modules over A. And I introduce the new notation, and we will denote this L of lambda. this simple model we will denote L of lambda. And moreover, we will see that this L, if we see L as a function from the set of simple modules over T to the simple modules over A, is a bijection. So this means that we can find all the simple module over A as a quotient, as the unique quotient of the proper standard modules, and every simple module over A is constructed in this way. This is related with your question, Corneli. Let me know if it's clear now. Okay, so we will start with the proof. And first, I want to recall something. I want to recall the following. Recall that if you consider if we consider the proper standard module over lambda as a B minus module, if we consider the proper standard module now as a B minus module, this is isomorphic to B minus tensor T lambda. This is by lemma. This is by lemma 3.8 that I proved. We proved it yesterday. This is an isomorphism in the category of B minus modules. And then we have a and we have a quotient. We have a yes, and we can go to the we project this, and hence an epimorphism to we can quotient by the ideal generated by the strictly negative degrees of B minus. Quotient by and this is isomorphic to the inflation, but now to the negative part, to B minus of lambda. That I mentioned yesterday when we draw this proper standard model like a triangle, and this is in degree 0, and we take out all of the negative degree. This is inflation. So I repeat, when we consider the proper standard model as a model over b minus, over the negative part, then it has a simple quotient, which is inflation of, which is lambda, viewed as a b minus model using deflation. And we will prove that, in fact, this is the only simple quotient of this model viewed as a b minus model. We come here for, yeah. Okay, so what we claim that, and we will prove that. So that is what we will prove. We will prove that this quotient that I mentioned before, that there exists of the proper standard model, is in fact the unique simple quotient of this proper standard model when we see this as a b minus model. And the proof is short. I don't want to say it's easy, but it's short because we will use a very important property of model, which is the Frobenius reciprocity. So let me write the proof of this claim. Okay. So we want to prove, in other words, we want to prove, we want to compute the head of, just to be emphasized, I am just writing the same, but instead using this restriction factor. And so we want to compute the head of this. So we will compute the morphism from this restriction to the simple models over b minus. So in order to compute the head of this model, it's the same that to compute all which morphisms there exist from here to the simple model over b minus. And the simple model over b minus are the inflation of the simple model of t. Because of the classification of that we saw yesterday between the simple module over T and the simple module over B plus, or is the same classification for the simple module over B minus. Okay, so we will compute this morphism. And when I say we compute the morphism, I mean to calculate the Hopf space. So we will compute Hopf, the morphism between the morphism as B minus modules. Let me write just B minus in order to write a little bit few. From where? From restriction from A to B minus of a proper standard module to inflation from T to B minus of mu. We will compute this Hopf space, and first we will do some replacement in order to compute it. First, we use this isomorphism that I mentioned before, which is the lemma 38. Which gives us an isomorphism of this restriction. It is isomorphic to B minus tensor T lambda. These are isomorphic because of lemma 38. Maybe you can see this. By the lemma 38, these are isomorphic. And the other inflation I left here, this is the fair replacement. And now here we have morphisms as B minus modules, and we have here this induced functor. And there is a very known property between the induced functor and the restriction functor, which is the Frobenius reciprocity, or in other words, that these functors are adjoint each others. And this means that compute this Hopf space is the same that compute the Hopf morphism as T modules of what? We replace this part just by lambda, and here we have to put restriction from B minus to T of inflation. Of mu. And this is Frobenius reciprocity. This isomorphism is known. This is a very important property which holds in general, and I made more explicitly in the list of exercise that I showed you at the end of the course, in order to prove this isomorphism, which is very important and very useful in a lot of parts of algebra, and is not difficult to prove. Okay, and now what we have to observe is that if you apply restriction to inflation, this is isomorphic to is just mu. So I will write this here, home t from lambda to mu. So restriction, I repeat this. If you apply restriction to inflation, this will be isomorphic to mu. It's like the identity. You obtain the same. So we wanted to compute all the morphisms as B minus module between the proper standard module and the inflation. And at the end, we saw that it is isomorphic to all the morphisms as T module from lambda to mu. And as lambda and mu are simple modules, this home space is 0 or is the Thiel, because we are at is the other assumption of the triangular decomposition is that the algebra is a split. This is the last assumption that I write yesterday, and we only use it here. So this is isomorphic to, this is the Thiel if lambda is equal to mu, or it is 0 otherwise. And this is by the fourth property of the triangular decomposition that I mentioned before, yesterday. So in resume, we have proved that if you consider we want to compute the head of this proper standard model as B minus model, and we have proved that the only morphism from here to a simple model, which is not 0, is only when mu is lambda. That means that the unique possible quotient of the proper standard model is, as B minus model, is the inflation of lambda. I will write this, but I can still put there the yeah. I will erase at the same time. You can copy this. Okay. So in conclusion, we have proved that the only possible simple quotient of the proper standard model as B minus module is inflation the inflation of lambda. So this means that the head of this module, I don't know if at the moment we don't even know if it is simple or not, but we know that it will be isomorphic to inflation, the head, but possible several copies of it. Maybe we have some copies of this model, but we will prove that actually there is only one copy. Maybe you can, what do you say, focus? And we will use the same trick that before. We will compute the home in order to see that we will only one copy of this n is only one. So first of all, we will compute as before home as b minus modules of restriction from a b minus to inflation. We will compute this in two ways. First, we know that this is isomorphic to the Thiel. We just proved that it is isomorphic to the Thiel. But now we can say that this is isomorphic to compute. It is the same to compute the morphism from here to here is the same that to compute the morphism from the head of this this is the same. This is the same because this is simple. So the only way to go from here to here, as this is simple, is through the head. So this is isomorphic is because this model is simple. Okay, but and now we put, instead of the head, we put what we think it is. It is a direct sum, n copies of this inflation. So here we use this isomorphism and put this is home from inflation lambda n copies of Thiel to inflation and okay, we have the same simple model, and here we have n copies. So this as a home, as an it is isomorphic to k to the n. Yeah, this is the same n up here. But if we see all this isomorphic together, we have that k is isomorphic to n copy of k, so n should be 1. And hence, we have proved what we wanted is that the head of the proper standard model viewed as minus module, B minus module, is isomorphic to inflation from T B minus. There is some question until here so far. Maybe we can we are just an hour. We are in the middle of the proof. Which I not could hear, but maybe you are something you need a rest. So maybe we can stop here and continue in 10 minutes. Okay, we will now to continue with the proof of the theorem. We have proved it. We have proven until now that the rest, if you see the proper standard module as a B minus module, it has simple head. And what we will prove now that the proper standard module has simple head in the cat as A module. What we will prove now. In order to do that, we will consider a module M, which is the sum of all the propers A submodules of the proper standard model. Why we consider this? Because if we can prove that it is proper, what mean by proper is that M is different from the proper standard model, is strictly contained, then this will imply that it is the only maximal submodel, and this is the only one maximal submodel. It will happen that the proper standard model has only one simple quotient, and this is because this equivalence between maximal submodels and simple quotients. Okay, and in order to see that it is strictly different to the proper standard model, we will use this part of this statement. So for that, we consider M as a B minus model. If we consider this as a B minus model, this is contained in the sum of all proper now B minus submodules of A of the proper standard model. Now if we see as B minus model, and that is because if you have a proper A submodule, it will be by restriction a proper B minus submodule. So this family that we are summing here is a subfamily of all these submodules. So this implies this contention. Yeah. And now the sum of all proper submodules is equal to the unique maximal P minus submodule of the restriction also of the proper standard model. And of course, this equality is because of that we write here. Yeah, this implies this equality. And I said before, this also because of this equality, this is different from the proper standard model. This is strictly different. So in particular, so let me write explicitly that it says that M is the proper submodule of the proper standard module, and moreover, as it is the sum, as M is the sum of all proper submodule, it is maximal, and it is the unique maximal because we are summing all inclusive the maximal, so in particular it is maximal. Moreover, M is the unique maximal A submodule of the proper standard model. And that is what we wanted, because therefore the quotient is the unique quotient, is the unique simple quotient of that in CA, in the category of models, of A models. In other words, the head of the proper standard model is simple. Yeah. There is some question? No? Okay. We will continue with the other parts. Okay. We will continue then with the proof. And now we will prove that there is a bijection. So we will prove now that this assignment between the simple models over T and the simple model over A is a bijection. First of all, in order to prove that it's bijection, we will prove that it is surjective and injective. First, we see that is surjective because or by the lemma 312. As we mentioned in the when we proved the lemma, we mentioned and we discussed that every simple module over A appear as a quotient of the proper standard module. So this means that, as we know now that the head is simple, we know that every simple module over A is the head of some proper standard module. This means that this map from here to here is surjective. So we will prove now that this map is injective. We will prove now. We will see. In order to see it is injective, we first analyze the graded case. So we will first to consider the category of graded models. Why we do that? Because we using the grading we will distinguish the simpler models. Because of this. Notice that we know that. Oh, notice. Oh, sorry. We have that. We have that. The following. We have from the proper standard model. We have two. We have the projection to L to the simple model. Yes, it is the head. And we have another projection, which proved at the beginning, to inflation. And this map is in the category of graded as B minus module. This is a map as A module, but we can consider it as a B minus module if we consider this just the restriction. And more space, but I will write the same. This is also in B minus. Okay, we have these two maps, and it is the unique simple quotient of this module. There exists a map from here to here. Exists in GB minus because this is the head. Because this is the head of this morphic of this model. It is the head in the category of P minus model. Okay. And why this is useful? Because in the lemma now, if the degree of lambda is d, for instance, then because of the lemma 3.9, we have, because of the lemma 3.9 that we mentioned yesterday, we have that the component of degree d of the proper standard model is isomorphic to, because of the commutative diagram, is isomorphic to also to the component of degree d of the simple model, and it is isomorphic to inflation, to this of to the inflation. So this is this isomorphism is because of lemma 3.9, and this isomorphism is because of this commutative diagram. So we can see now that if you have two, I will write this, but you can see now that by looking in the component of degree d, which is the component of maximal degree of the proper standard model, we can distinguish the simple models. Therefore, if L lambda is isomorphic to L mu, then lambda is isomorphic to mu, because of this that I write here, because of this isomorphism. And then what we proved? We proved that if two simple models corresponding to lambda and mu are isomorphic, this only occurs if lambda and mu are isomorphic. And this is the same to say that this map here is injective. So in the case of graded models, we have proved that L is injective and surjective. And then it is bijective as we wanted. It's a bijection. Is some question or comment? Yeah, Francisco. Yes, this I proved that. I read a little bit few. We proved that really between this implication we have to go to here and then to here. Is are isomorphic as P minus model. They are isomorphic as T model. Thank you. Okay. So in order to finish the proof, we have to analyze the case where the ungraded case, where instead of G of A, we have M of A, just the model as ungraded. But this will follow easily because we will use very important result, Gordon and Green. Now, to prove that L is injective, for the category of ungraded module, we use the result of Gordon and Green. This is another paper that I sent you in the email. There is 2 papers of Gordon and Green, where in particular they prove that ensures that we can endow L lambda with the grading that say we can there is a grading that we can see L in the category of graded modules. So as a module is L, but there is a gradient, there is a decomposition such that in degree 0 is equal to lambda as or in category of T modules. Hence, and now we can use that we have proved for the graded case. So if L mu and L mu and L lambda are isomorphic, then are also isomorphic the graded version of them. And then we use, so this is Gordon and Green, and this is the graded case that we proved before. So this is because we are in the category of graded modules. Then and this is lambda and this is mu. So if we start from two simple equations of the proper standard model of lambda and the proper standard of mu, which are isomorphic, this is the only way that it is occur is that lambda and mu are isomorphic. Therefore, L is also injective in the category of ungraded models of 4. And this finishes the proof, and this finishes the proof of the theorem. This we have proven now that this L the assignment between simple module over T and simple module over A, given by take the head of the proper standard module, is a bijection. Let's finish the proof of the theorem. There is question, comments. So if there is no question, I would like to discuss some outcome of this theorem, another way, and also another way to read this theorem in order to emphasize the importance of it. So let me give some remarks. First, as we can note that as T is concentrated in degree 0, if lambda is an irreducible module, the category is a simple module as graded T module, then lambda is also concentrated in some degree. So that means that lambda is just equal to the homogeneous component of degree D of it. We don't have a direct sum decomposition bigger here. We don't have more components because T is in degree 0. Because if we want another direct sum decomposition, then lambda will not be simple. As a consequence of this, first remark is that L of okay, in this case, then L of lambda, when we see it as a graded T module, it is isomorphic to lambda, which is in degree here in degree D, plus some other component which has degree smaller than D. This is in the category of graded T models. And this is by lemma 39. This is because of the lemma 39. And this is part of the proof that is part of what we see before, that in D it's lambda, and we have things or degree smaller. And another thing that I want to emphasize is that L lambda is generated as B minus module by lambda. And this is because the proper standard model also satisfies this property. So these are two very important properties of the simple model. And now I would like to this is a corollary of the theorem. That is not, there is nothing to prove. It's mostly to read. It's another way to read the theorem, and it is this: L lambda is the unique. Is a characterization of this simple model. Is the unique simple A module which is generated by a B plus module isomorphic to the inflation from T to B plus of lambda. So that means that I will emphasize that that means that lambda is a tensor module of lambda such that when you act by the ideal of strictly bigger than 0 by lambda, you will obtain 0. This is another way to characterize. This is a consequence. It follows from the lemma 312 and the theorem. This is another way to read these two results together. It's a characterization. So in other words, you have a simple model over this algebra with the triangular decomposition such that there is a model satisfying this property, then it should be the head of the proper standard model corresponding to lambda. There is some question. Now I will. What time it is? 45:06. Okay. Now I will write a conclusion, another conclusion of what we did until here so far. So what is a fair conclusion? That we have a classification of the simple model. It's just to repeat and emphasize what I did in order to fix it and in order to clarify what we did. Okay, so let me denote by lambda bigger the family of representatives of isomorphic classes of isomorphic classes. Let me write in ME in the category of modulo over A. So then this set, if we form the set of all simple model or all the head of the proper standard model of lambda in this lambda bigger, is a classify or is a complex set of non-isomorphic simple A models. So that means that this set classify all the simple model. We have a classification of the simple model, and this is important because the simple model are the smaller pairs in the category of model, and we have this classification. It's very important. For the moment, we only have the classification. Okay, in order to continue the study of the category, will appear naturally a very obvious question. Now we can pose some problem. Give more information about the structure of each lambda, because we didn't know explicitly the action. We only know that it is simple, but we didn't know how A acts over it. But okay, a first problem is give more information about them. For instance, a natural question is describe L lambda as a T model. That is a natural question, and it's inspired also in other contexts, because in this theory we have for that we know about Lie algebra and enveloping Lie algebras. This is the same idea. From there, one construct the simple modules in this way, and then one try to describe this simple quotient as a module over the Cartan subalgebra, and in this context, the T is like the Cartan subalgebra. So describe L lambda as a T module is the next step in order to have more information about the category of a model. We of course we could we cannot to do this in general, because this algebra with triangular decomposition can be very different between them, but we can give some path from where to start to study them, and that is what we do tomorrow.